Assalamualaikum and good day. I am Saidatun Ashatun Sakina, representative from our group. We'll be presenting numerical simulation of one-dimensional solar cell model. As we can see, the usage of photovoltaic is increasing along the time. And the photovoltaic is a fast-growing market, especially when now RMK11 Malaysian is encouraged to use a PV at their homes and being advantaged with feed-in tariff. So right now, silicon wafer-based PV technology account for about 95% of the total production in 2019, whereas 66% of it is monosilicon technology. So this is a very significant contribution towards the global energy system because of the constant improvement of conversion efficiency and also low cost of modules and system productions. So this purpose of the journal is to establish the solar cell modeling in blend phase through numerical analysis and to analyze the performance of monosilicon solar cell material for different thickness. Based on the motivation and problem statement of this project is, the modeling of solar cell are the most convenient method used for solving and studying about the efficiency of solar cell. So this is very important because from the simulation of this modeling, we can analyze the hole density and current density. And the diffusion advection equation can contribute to performance of a solar cell. So in this project, we limit to cover the blend phase only and neglect the charge transport in acceptor and donor phase. Solar cell mechanism and its mathematical modeling. So basically, the mechanism is about the working principle of the solar cell. So we do have donor phase, blend phase, and acceptor phase. So when the sunlight hit the blend phase and absorbed, the generation of carrier begin to happen. So at this interface, only one type of carrier is allowed to enter the phase. So for example, at the donor phase, only p-type, which is hole carrier, is allowed to enter. And at the acceptor phase, only n-type is allowed to enter here, which means electrons. And this is the semiconductor model equation for the blend phase. Semiconductor model equation consists of Poisson equations, drift diffusion transport equation, which is current density, and continuity equation, where P and M are the density of electrons and holes, while J is the current density for electrons and holes, and G is the generation, while R is the recombination. The boundary condition of equation 1 until equation 5 are listed as follow, which consider x equal to 0 up until x equal to L. So when x equal to 0, we consider Px equal to n equal to 0, and the potential volt difference is V naught. While at x equal to L, and x equal to P equal to 0, and the potential difference assumes 0 at this point. So in the initial condition, where T is equal to 0 in here, both of charge carrier equal to pi naught, which is charge density at the equilibrium state. So after that, we proceed to the numerical simulation. Through the process of the discretization of special dipole, we convert the PDE into a set of ODE, which we call that method of 9, which can be solved using built-in ODE solver in MATLAB by using finite difference approximation technique. For the result and discussions, now we can see the comparison of electron density between simulation and experimental data. So based on the result, there is a simulation and reference. Why is the difference occur? Because we solve the model is in blend phase only, and the charge transport at the donor phase and acceptor phase is neglected. So when the charge separation occurs at x equal to 1, where which x is the thickness, where electrons diffuse into the acceptor region justified by the large jump in electron affinity between the blend phase and acceptor phase. For the section hole density against thickness, where when x equal to 0, the active layer at the interface allow the transport of holes and block the other to across in the donor phase. The bulk electrons holes carrier density are significantly concentrated in the blend phase as reacted upon the light absorption by monosilicon. For the result and discussion, for the current density and versus voltage characteristic curve of silicon solar cell with different thickness, it is found that 25.5% efficiency on the monosilicon solar cell of thickness at 0.25 micrometer, and the efficiency reduced to 16.2% with the decrease of thickness of solar cell at 0.15 micrometer. For the conclusion and future work, so we can say the drift diffusion model of one-dimensional solar cell in blind phase is presented and is solved numerically, and we can know the charge density of holes and electrons behavior across the thickness. The smaller the thickness of the cell, the lower the cell efficiency. And we can say that this model will be useful for a guideline of the thickness of cell that predicts the monosilicon solar cell performance. And for future work, we would like to extend the modeling of solar cell for the blend phase to acceptor and donor phase. Thank you.